Hello everybody, I am back with some more notes. I'm on page 10 now. I may post a homework help video for page 9 in the worksheet here in a little bit, or at least a key so you can start checking your answers. But we're going to kind of leave convergence for a minute and start talking about something called a Taylor-Maclaurin series in polynomials. This is kind of the second big half to our series unit. So the first half is talking about determining whether series converge or diverge and the radius and interval of convergence. And then the second half is talking about constructing series or polynomials to approximate different functions. So I am going to be doing some of the examples from the packet, but you'll probably also want some notes so that you can write down some definitions and formulas and things like that. So today, I guess you can title your notes Power Series. Or maybe that's not the title of our notes, but that's our first definition. So you could call this Taylor and Maclaurin Series Day 1, I suppose. Let me see if I can keep this from autofocusing all the time. Okay, so first we need to talk about what is a power series. So an expression.
Hey, I can't see what you're writing with your hand on it.
Of the form.
I'm watching what you're writing. From?
It's not from, it's form. Okay, my daughter's here trying to get a calculus lesson too, but she's going to color quietly, right? Okay, so an expression of the form sum from n equals 0 to infinity of c sub n times x to the n. That is a power series. So c sub n could just be any other series. So normally I use a sub n, but here I'm using c sub n. And then it's multiplied by an x to the n. So whenever you have that x to the n involved, that's what makes it a power series. So if we were to expand this out, and it does start at 0, notice that. First thing we would do is plug in a 0 for n. So I would have c sub 0 times x to the 0. Wasn't x to the 0 just 1? Yes, it is. So I just have c sub 0 plus, then I would have c sub 1, x to the first, c sub 2, x squared, plus dot, dot, dot. So as you can see, this actually would give you a polynomial. Polynomials are functions with terms added or subtracted together where you have x to different powers. And so this is what we would call an infinite polynomial because we have x squared and we would go up to x to the 100th, x to the millionth, etc. So that's kind of a new thing, an infinite polynomial. So an expression of this form is a power series centered at x equals 0. And we're going to talk more about this whole centered at x equals 0 thing. So an expression of the form the sum from n equals 0 to infinity of c sub n times x minus a to the n. So notice now I've shifted over a units. So that'd be c sub 0, because still when I plug in a 0 here, anything to the 0 power is 1, plus c sub 1 times x minus a to the first, plus c sub 2 times x minus a squared, etc. So if it's in this format, that is a power series centered at A. Okay, power series centered at 0, where it's just the x, and a power series centered at A is whenever we have subtracted that there. Okay, so let's just for a minute consider the power series. The sum from n equals 0 to infinity of x to the n. So our most basic power series. where the C sub n series would just be equal to 1. So our most basic power series, this power series, converges when -1 is less than x is less than 1. So it converges as long as x is between -1 and 1, because really what this is a geometric series. Okay, so when x is between -1 and 1, we'd have fractions raised to the nth power. So it'd be like absolute value of r less than 1. So you can kind of think of x as your r in the geometric series here. So this converges when x is between -1 and 1, because it's like a geometric series. Not including -1 and 1, right? If I plugged in a -1 for x, -1 to the n, that series does not converge. It goes back and forth between -1 and +1 forever. So if you think about it going -1 plus 1, -1 plus 1, -1 plus 1, you're never going to converge to one value. And then 1 to the n would just be 1 forever. So 1 plus 1 plus 1 plus 1. So that would go towards infinity. So not including the endpoints, it converges when x is between -1 and 1. And the infinite sum, remember, of a geometric is a sub 1 over 1 minus r. So in this case, let's think about this. A sub 1, just think of that as your first term. So plug in the first number for n. So when I plug in the 0 for n, I get x to the 0, which is actually 1. And then here, this x is taking the place of the r. So the infinite sum of this series is 1 over 1 minus x, which means that this series converges to this function, 1 over 1 minus x. So this infinite series, which is the sum from n equals 0 to infinity of x to the n, which remember that would just be 1 plus x squared plus x cubed, dot, dot, dot. This infinite series actually converges to, or equals, if you could do infinitely many terms, it would look the exact same as 1 over 1 minus x. That is kind of crazy. So what I'm going to do is I'm going to actually show you that this is true, that this infinite series converges to 1 over 1 minus x, meaning the more terms you do, the closer it's going to be to 1 over 1 minus x. I am going to. So what I'm going to do is I'm going to go to my graph. I'm going to show you this. Oops, need to change my mode back to function mode. So in y1, I'm just going to put the first two terms, so 1 plus x. In y2, I'm going to put three terms, 1 plus x squared. In y3, I'm going to put 1 plus x squared plus x to the third. And then in y4, I'm going to go all the way up to x to the fourth. Plus x squared plus x to the third plus x to the fourth. Okay, so let's zoom 6, look at this so far. So 1 plus x is obviously just going to be a straight line, right? We would call that the first degree polynomial. 1 plus x squared is a parabola. Okay, we're thinking so far probably those don't look like 1 over 1 minus x. The next one looks like that, a cubic, because it goes up to x cubed. The next one looks like this, a fourth degree polynomial. But you will see there's this little area in here, right in there. Oops, I actually drew on my calculator. There's this little area in the middle, if you can see that. Oh no, the lighting is terrible. Okay, where they do all look pretty close to the same thing. And remember, this only converges when x is between -1 and 1. So we're saying that this polynomial will equal this function only between -1 and 1. So what I'm going to do, now I'm going to type in the real function. Yes, Leslie. 1 over 1 minus x. And I'm going to change my window now to just look from -1 to 1. And I'm going to go to the y's like maybe -2 to 2. Okay, so there's the one that's just a straight line. Then when we include the x squared, we get a cubic. Sorry, I'm hoping you can see this a little better. The lighting is so bad. Okay, let me get... Let me see if I can darken this up a little bit. Oh, that's too dark. There we go. Okay, so notice right here close to 0, they're all the same. They all equal 1 because this will be a polynomial or power series centered at 0 because it doesn't have that x minus a. So right around 0, they're all the same. And between -1 and 1, they're all close. Definitely not equal. But you can see that this, the more terms we have, the more accurate our polynomial is going to be. So the idea is that if I had infinitely many terms here, it would actually look exactly the same as 1 over 1 minus x as long as I stay between -1 and 1. So it's a really cool concept, actually. It's like a little bit mind-blowing. So what we're going to be doing is we're going to actually kind of go the other way. We're going to take functions like sine x or 1 over 1 minus x or whatever, and we're going to come up with an infinite polynomial that would look like that function. So that's kind of our end goal here. But before we get to that, we are going to construct a polynomial to fit certain specifications. So I'm going to make a couple little notes here. Let me zoom out a little with my camera. Okay, so one little note to make is that we will be constructing power series to represent a variety of functions. So that's kind of our end goal here with power series. So first, for our first example, we will construct a polynomial to fit certain specifications. So that's kind of the precursor to finding a power series to represent a function, is knowing how to actually make a polynomial that has certain characteristics. So that's what we're going to practice here. So this is actually the example that's on page 10. So I'm going to write out the directions though. Construct a 4th degree polynomial. What, babe? Yeah, that's a P.
Why do you do that?
Because I was telling him it's on page 10. Sorry, answering my daughter's questions. I'll answer your questions later, okay? Construct a 4th degree polynomial f of x, where f of 0 equals 1, f prime of 0 equals 2, f double prime of 0 equals 3, f triple prime of 0 equals 4, and the 4th degree polynomial, or the fourth derivative at 0 is 5. So that's all I'm telling you. I'm telling you the function value at 0, first, second, third, and fourth derivatives at 0. And using that information, you should be able to come up with a function that fits all of this criteria. So the way we're going to do this, we're going to start with the 4th derivative. So start with the lowest derivative. Start with the 4th derivative, or of x, sorry. And we're going to basically just integrate until we get to f of x. So we should be able to find our solution by starting with the 4th derivative and just integrating a bunch of times. Okay, so that's what we're going to do here. Let's get my paper up. So I know the 4th derivative at 0 is 5. So we're just going to say that that's our 4th derivative because we don't know anything else about the 4th derivative. Okay, that's all we know. So that's our starting point. To get to the third derivative, f triple prime, we would integrate this. So the integral of 5 is 5x plus c, right? So this is where we'll use our third derivative, plug that in to solve for c. So if I plug in the 4 for y and the 0 for x, I end up getting c equals 4. So that my third derivative is 5x plus 4. Now I integrate again to get f double prime. Okay. So integrating this, I would have 5x squared over 2 plus 4x plus c, right? And I need to solve for c using the second derivative now. So second derivative at 0 is 3. So if I plug in a 3 here, and then 0 plus c, then c is going to equal 3. So I have f double prime of x equals 5x squared over 2 plus 4x plus 3. Okay, so I'm going to come up over here. Now I need f prime of x. So I'm integrating one more time. Now I have 5x cubed over 2 times 3, right? So over 6 plus 4x squared over 2, which of course I could reduce that, plus 3x plus c. Okay, so now I use the first derivative. F prime of 0 is 2. So if I plug in a 0 here, and that equals 2, c is going to have to equal 2, just like on the previous ones. So I have f prime of x equals 5x cubed over 6 plus 4x squared over 2. I'm not going to reduce this, and I'll tell you why in a minute. Okay, so plus 3x plus 2. And finally, we're going to get to f of x. I'm not reducing it because I want us to be able to see some patterns here in a minute. So integrate one more time. 5x to the 4th over, and then we do 6 times 4, right? So it'll be 24 plus 4x cubed over 2 times 3, so 6, plus 3x squared over 2, plus 2x plus c. And now we use f of 0 equals 1 to find c, so c equals 1. So f of x is 5x to the 4th over 24 plus 4x cubed over 6 plus 3x squared over 2 plus 2x plus 1. Okay, so I could, of course, reduce this, but I'm not going to. So what I want to actually try to do now, this would be our answer, by the way. We have found a polynomial that's 4th degree, meaning it goes up to x to the 4th, that has all of these conditions. F of 0 equals 1, check. So derivative at 0 equal 2, check. So we've come up with this solution here. Just for fun, I want to try to write this as a power series in sigma notation. Wouldn't that be fun? So if I want to try to write this as a power series, I'm going to first flip the order around, because normally we'll start at x to the 0, x to the first, x squared. So I'm just going to write it like this. 1 plus 2x plus 3x squared over 2 plus 4x cubed over 6 plus 5x to the 4th over 24. Okay, so I'm going to start at n equals 0, and I'm going to go up to n equals 4, because I'm just stopping there. So this one's not infinite. Okay, I have a beginning and an end. This is fun, writing a polynomial in sigma notation. Isn't that fun? Okay. So let's see, the 1, 2, 3, 4, 5, that part of it all, that's just n plus 1, right? So the constant part, the coefficients are n plus 1. And that's just because I picked convenient numbers whenever I gave you this example, so that it would follow a pattern. It doesn't have to follow a pattern, but this time it does. So the coefficients are always n plus 1. And then I have the x part, right? X to the 0, x to the first, x squared, x cubed, x to the 4th. So I have x to the n. And then I have these denominators. I've got to figure out something to do for these denominators. Well, The first two don't have denominators, so they're both over 1. So let's ignore that for a minute. Then I have a 2, so 1, 1, 2. Then I have a 6. Let's think about how we got this 6. We got this 6 by doing 2 times 3, because when I integrated, I had to divide by 2, then I had to divide by 3. So this 6 was actually 2 times 3. Okay, this 24, how did we get that? Well, we actually did 2 times 3 is 6, times 4 is 24. We actually did 2 times 3 times 4, because we integrated 3 times. So we went from x squared to x cubed to x to the 4th. So we had to divide by all 3 of those numbers. So we have a special symbol for when I'm multiplying consecutive numbers, and that's a factorial. So I would be cool if this could be n factorial on the bottom, but we still have to make sure it fits for the previous terms. And it turns out it does, because when we start at n equals 0, 0 factorial is 1. It's like the weirdest math fact, but it's true. 0 factorial is 1. You can try it in your calculator, and you will get 1. 1 factorial is 1, so it works for both of these. 2 factorial is 2. 2 times 1. This is 3 factorial. 3 times 2 times 1. This is 4 factorial. 4 times 3 times 2 times 1. So n factorial there. So this is why factorials become important with series, because actually when we integrate multiple times, we're actually going to end up with factorials in our denominators. So those will continue to pop up. Super cool. Okay, so let's now go ahead and do a couple more definitions. So if you want to switch back over to your notes or squeeze it in also on page 10, that's fine. So we're going to kind of generalize what we saw on this previous example to other functions. Okay, so using derivatives at 0, as we saw here, using derivatives at 0 is one method of constructing a polynomial. So that's kind of what we're going to do when we try to find a polynomial that represents a given function. So in general, f of x will always equal f of 0 over 0 factorial times x to the 0 plus f prime of 0 over 1 factorial times x to the first plus f double prime of 0 over 2 factorial times x squared. So you see the pattern, right? So we have f of 0, f prime of 0, f double prime of 0, which that was taken care of by our n plus 1. The bottom we have the n factorial, and we have the x to the n. So in general, a function will always equal this if you know or are given function and derivative values at x equals 0. So anytime you're given function and derivative values at x equals 0, you can construct a polynomial of this format that meets those criteria. So we will use this idea to generate power series to represent functions. Sorry, I'm kind of slanted there. Okay. Polynomials that follow this format are called Taylor polynomials. Okay, Taylor polynomials. If centered at x equals 0, like what we did above, right? Because we found the derivatives and everything at 0. So if centered at x equals 0, then they have a special name they are called Maclaurin polynomials. Oh my gosh, I just spelled Paul like the name Paul. I'm losing my mind. Okay. Polynomials. Nomials. Oh my gosh. Spelled this word a jillion times and for some reason I'm having trouble. So they're called Maclaurin polynomials if they're centered at 0. Okay. So today we're just going to be focusing on Maclaurin polynomials centered at 0 to get us started here. And we're going to come up with the Taylor or the Maclaurin polynomial for some really common functions. White blank papers? No, you'll have to go get some from the office. Okay, so for our example, like I said, we're going to come up with the polynomial representation for some common functions. So our first example, we're going to write a Maclaurin polynomial I'm going to say do a 4th order, meaning we're going to go up to the 4th derivative to approximate f of x equals e to the x. So this is our first one we're going to look at, e to the x. A common function that we see a lot. So after we write our 4th order polynomial, then we're going to write it in sigma notation. So then write the infinite Maclaurin series using sigma notation. Okay. So we're going to do this by finding the function value at 0 and up to the first 4 derivative values at 0. So here's what we're going to do. We're going to find f of x is e to the x. We're going to find the first derivative, which with e to the x, still e to the x, right? Second derivative, third derivative, and 4th derivative. So with e to the x, super easy. It's always e to the x. And now what we're going to do is we're going to plug in x equals 0 because these are Maclaurin polynomials centered at 0. So all of these, when we plug in 0, e to the 0 power is 1. Yes. Okay, so we get 1 for all of these. And what we're going to do is we are going to follow this pattern that I wrote up above. So we take f of 0 over 0 factorial times x to the 0 plus f prime of 0 over 1 factorial times x to the first. And because that's always what you're going to get whenever you start with the 4th derivative and then integrate. Okay? So we're going to say e to the x is approximately equal to the first derivative, so that's 1, over 0 factorial times x to the 0 plus the second, or sorry, that's not the derivative at all. The function value is your 0 term. Then the first derivative, so 1 again, over 1 factorial times x to the first. Plus the next derivative, so they're always 1, over 2 factorial times x squared. The next derivative over 3 factorial times x cubed. And the 4th derivative over 4 factorial times x to the 4th. Rose is awake? Huh? She's asleep, yeah. Okay, so we get this polynomial, but I'm going to kind of clean it up a little bit. So this is just 1, x to 0 is 1, so that's literally just 1, plus this here is just 1, so that's x to the first, plus, I'm going to rewrite this as x squared over 2 factorial, plus x cubed over 3 factorial, plus x to the 4th over 4 factorial. Okay, so this would be our 4th order or 4th degree polynomial approximation of e to the x. So this is kind of that first answer, the Maclaurin polynomial to the fourth term. Then it also says write the infinite series using sigma notation. So we have the sum from n equals 0 to infinity. And just always think of it as having those three parts. It has the parts that's the derivative, the part that's the factorial, and then the part that's the x. So this one, if we look at the simplified version here, it's just x to the n over n factorial because these coefficient terms are all 1. Okay, so here is the sigma notation for e to the x. And this, by the way, you can write out, I don't know if I told you, on page 11, where it says number 1, right here, e to the x. So some basic Maclaurin series, e to the x equals, and then the next one's 1 over 1 minus x. We're going to do all of these together. Okay. You want to show them? Here is a picture my daughter's been working on while I was giving notes. Isn't it great? She colored it. She cut it out. She knows the rainbow order perfectly. She did a great job. There you go. Okay, so what we're going to do is we're going to go through the other common functions on pages 11 and 12 together. So I guess before I do that, though, I want to show you that this polynomial here is going to look similar to e to the x. Now, it would look exactly the same as e to the x if I had infinitely many terms, but I don't. I only am going up to x to the fourth. So in y1, I'm going to graph e to the x, and in y2, I'm going to graph that answer that we just got. So 1 plus x squared over 2 plus x to the third over 3 factorial, which is 6, plus x to the fourth over 4 factorial, which is 24. So, and let's go back to our standard window. Let's just see what we get here. So this is e to the x right there. And then our fourth degree polynomial should be coming. And wow, so look, looks really good over here. Of course, not as good here. So what's going to happen is the more terms you have, this red line is going to kind of start to flatten out and be more, be closer and closer to that e to the x graph. So pretty cool. Okay, so next we need to look at number 2. So we're on page 11 now. Number 2, which is 1 over 1 minus x. I guess I'll just go ahead and start working on them over here. Okay. So we're going to do it the same way. We're going to write out f. So that's 1 over 1 minus x, f prime. So let's see. 1 over 1 minus x is the same thing as 1 minus x to the negative 1. So when we do the derivatives, let's do it like this. Think of the 1 minus x to the negative 1. So we'd have negative 1 minus x, but times negative 1 because of the chain rule. Okay. To lock the focus again. Okay, so times another negative 1. So it actually ends up being positive 1 minus x to the, to the negative 2. Okay, then f double prime. So we bring down the negative 2. So negative 2 times 1 minus x to the negative 3 times negative 1 again for the chain rule. Okay, so I have 2 times 1 minus x to the negative 3. Now the third derivative, not yet, is going to be negative 3 times 2, so negative 6 times 1 minus x to the negative 4 times negative 1. So once again, that double negative makes this positive 6 times x minus 1, or sorry, 1 minus x to the negative 4. Last time, fourth derivative. So I'm going to go to 4 derivatives each time. So negative 4 times 6 is negative 24 times 1 minus x to the negative 5th times negative 1 again for the chain rule. So we get positive 24 times 1 minus x to the negative 5th. Okay, so there are my first 4 derivatives. And now I need to find all of those values at x equals 0. So at x equals 0, f of x, when I plug in a 0 here, I would just get 1 minus 0. So I have 1 to the negative 1, which is just 1. Here, plug in a 0 for x, I get 1 to the negative 2. So that's 1 to the negative 2. 1 to any power is 1. So 1 again. Plug in a 0 for x here. 1 to any power is 1, like I said. But then it's times 2. So I get to get 2. 1 minus 0 is 1 to any power is 1 times 6. And so for the same reason, when I plug in a 0 down here, I'll just get 24. So here are my values at x equals 0. So when I write out my polynomial, I guess I should have left some room to write it here. Whoops. Just write it over here. So I have 1. Remember, the first term is your coefficient, which comes from your derivatives, coefficient times x to the 0 over 0 factorial. So, which is x to 0 over 0 factorial always equals 1. So I have 1 plus 1x to the first over 1 factorial. I'm not going to write that. Plus 2x squared over 2 factorial. Plus 6x to the third over 3 factorial. So it's always like x squared over 2 factorial, x cubed over 3 factorial. And then plus 24, x to the fourth over 4 factorial. And if you're kind of getting confused and wondering, why do I do the 2 over 2 factorial, the 3 over 3 factorial? Go back and look at that first example we did, and you'll see that whenever we did it the long way, we started here and integrated up, it looked like this. Okay, so that's where this is coming from. So here is what we get, but actually this can reduce because 2 and 2 factorial, those are the same thing. 6 and 3 factorial, those are the same thing. And 24 is equal to 4 factorial. So that will actually always happen here. So this power series is just 1 plus x squared plus x cubed plus x to the fourth. Okay, so if we want to write that in sigma notation, the sum from n equals 0, let's just go to infinity if we were going to keep going, it would just be x to the n. And if you go back to the beginning of your notes, you'll see that I told you that the power series x to the n should converge to 1 over 1 minus x because it's a geometric series. And look, there it is. Very cool. And so what I didn't say a minute ago is that these 5 basic Maclaurin series that we're doing, so we did e to the x, we're doing the 1 over 1 minus x, and we're going to continue on. These 5 things are going to be ones that you have to have memorized. They're very commonly used and manipulated in different problems, so you need to start working on memorizing them. So you would memorize that the function 1 over 1 minus x is equal to the series x to the n. All right, next, natural log 1 plus x. So we have f is the natural log of 1 plus x. F prime would be 1 over 1 plus x, right? That's the derivative of natural log. Okay, which is the same thing as 1 plus x to the negative 1. So f double prime would be negative 1 plus x to the negative 2. F triple prime would end up giving us positive 2 times 1 plus x to the negative 3. I'm using the chain rule, but the derivative of the inside is 1, right? So we don't actually have to do anything here. And then the fourth derivative would be negative 6 times 1 plus x to the negative 4. Right? Yeah. Okay. So then if we plug in x equals 0 for all of these, so plug in a 0 here, then the natural log of 1 is 0. So this is at x equals 0. For this one, I plug in a 0, and 1 to anything is 1. Plug in a 0 here, 1 to anything is 1, but then there's this negative here. So I get negative 1. Once again, I have 1 to the negative 3 once I plug in a 0 for x. So I just get 2. And this, I would just get negative 6. Okay. One thing to notice is this looks like it's alternating. Positive, negative, positive, negative. And it should continue to do that. If we found the fifth derivative, you'd have negative 4 times 6, so you get positive 24. Okay, so if we want to write this out, my first term is 0. So we can actually just leave that off, but I'll put the 0 plus to start off with. Then I have 1 times x to the first, so just x. Then I have minus 1 times the x squared over 2 factorial. Then I have plus 2 times x cubed over 3 factorial. And then minus 6 times x to the fourth over 4 factorial. Okay, and if we wanted to keep going, let's just go ahead and keep going. One more term to help us see the pattern here. The next one will be 24 x to the fifth over 5 factorial. So let's try to write this in sigma notation, and we can go ahead and get rid of the 0. But when we want to write our sigma notation, I still want to start it at n equals 0. So this time my n equals 0 term will actually lead to the x here. Or you could write it at n equals 1, but to stay consistent so they all start at n equals 0, I'm going to do that here too. Okay, so the coefficients are 1, negative 1, positive 2, negative 6, positive 24. So I'm just going to ignore the plus and minus for now. So I have 1, 1, 2, 6, 24. So that actually looks like n factorial, okay, because n factorial would give you 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. So that's the top. On the bottom, I'm starting with 1 factorial, not with 0. So on the bottom, I need to write it as n plus 1 factorial. Okay, see how they're staggered by 1? This is 2 factorial, this is 3 factorial. This is 3, this is 4. This is 4 factorial, this is 5 factorial. So the bottom is 1 greater factorial than the top. And then I have the x to the n plus 1 also. And then I haven't taken care of this alternating bit. So I also need to have negative 1 to the n. Let's see, make sure it should be n or n plus 1. But at n, starting at 0 to 0 power would give you a positive 1. So that should work out. And while this looks nice, I would like to try to reduce these factorials. So I'm going to rewrite on the bottom that n plus 1 factorial as n plus 1 times n factorial. Then we have times the x to the n plus 1 times negative 1 to the n. And that allows me to cancel it out. So I get my final answer for the sigma notation as, let's see here, x to the n plus 1 times negative 1 to the n over n plus 1. Okay. Some people might write it in a different order, but essentially here we go. Here's our power series, our Maclaurin series for natural log of 1 plus x. So we've got a couple more here, 2 more, which are the most fun, right? Sine and cosine. Yes, yes, yes. They're not going away. Still have to know them. Leslie, will you please stop? About 5 more minutes, okay? No, it's not going to be 6 hours. Okay, so here we go. For sine x, let's look at lots of derivatives here, actually. So we have f of x is sine x. F prime is cosine x. F double prime is the derivative of cosine. Negative sine x. F triple prime is negative cosine x. The fourth derivative then would be positive sine x. So now we're back to the top of our cycle. Let's do a few more. The fifth derivative then would be back to cosine. Sixth derivative, I'm going to go up to 7. Be negative sine again. And the seventh derivative would be negative cosine x. And obviously feel free to pause if you're taking longer to write these than I am, because I know I'm going kind of fast here. Leslie's getting bored. Okay, so at x equals 0, plugging in a 0 for all of these. What's the sign of 0? You can't respond to me, I just realized. The sign of 0 is 0. Cosine of 0 is 1. Sine of 0 is 0. Negative cosine 0 will be negative 1. Sine of 0 is 0. Cosine of 0 is 1. Negative sine 0 is still 0. Negative cosine 0 is negative 1. So kind of has this pattern, 0, 1, 0, negative 1, 0, 1, 0, negative 1. So when we go to write out our terms, we're not going to have any constant term at the front. That's a 0. This one goes with our x term. So I have 1x over 1 factorial. And then I have 0 on the x squared. So think of this as being your constant, your x term, your x squared, your x cubed, your x to the 4th, your x to the 5th, x to the 6th, and x to the 7th. Okay, think of it like that. So I have no x squared term. Then I have negative 1, so I'm just going to put minus of my x cubed. Don't forget over 3 factorial. Nothing for x to the 4th, be times 0. Then I have plus my x to the 5th. Nothing x to the 6th. And then I have minus x to the 7th. So do you see that pattern? It's just the odd powers of x. So when I go to write that in sigma notation, once again, I want to start at n equals 0. Oh, so cute. Okay. On the top, I just have x to, well, first of all, it's alternating. Let me put that out in the front. I'm sorry. So I'm going to write negative 1 to the n. So it starts positive, so that should work. And then I have x to the, and these are odd powers. They go up by 2 each time, right? The way to make an odd number is like this, 2n plus 1. Think about it. Plug in a 0 for n, you would get x to the 1st. Plug in a 1 for n, you get x to the 3rd. Plug in a 2 for n, you get x to the 5th. So you can see that that would work. X to the 2n plus 1. Over, and it's the same numbers on the bottom, but factorial. So 2n plus 1 factorial. And there is your power series for sine. And like I said a minute ago, this does have to be memorized. Both the expanded version like this and the sigma notation. I love it. You want to show it? Okay, Leslie's taking a picture off the wall and she wants to show you guys. So here it is. Isn't it beautiful? Thank you, Leslie. Okay, last example is cosine. It's going to be really similar to the sine one as far as it's going to be a pattern like that. Except obviously we'll get something slightly different when it's cosine instead of sine. So last one here, cosine x. So I'm just going to start listing off. F of x is cosine. F prime is negative sine. F double prime, not yet, is negative cosine. F triple prime is sine x. And then the fourth derivative is cosine x. So I'm going to keep going through 2 complete cycles. The fifth derivative is negative sine x. The sixth derivative
I just want to do colors.
Is negative cosine x. Seventh derivative is sine x. Why not? One more. The eighth derivative is cosine x. Back to where we started finally. My goodness. Okay. So I know I did that quickly, but you can see it's just that pattern taking all these derivatives. So now at x equals 0. For all these, cosine of 0 is 1, sine of 0 is 0. So the negative cosine of 0 is negative 1. Sine is 0. Cosine is 1. Sine is 0. Cosine is negative 1. Sine is 0. Cosine is 1. So you see the pattern. Remember, it starts constant term, x, x squared, x cubed, x to the 4th, etc. So when I go to write it out, my polynomial, I have 1. Then I don't have an x term. Then I have a minus, and that's my x squared term. Plus, this is my x to the 4th term. And then minus for my x to the 6th term. And plus again for my x to the 8th term. Okay, so this is our expanded version. So with sine, it was odd numbers. Cosine, it's evens. So when I go to write the sigma notation, it's still alternating. So I still have that negative 1 to the n. And it starts positive, then negative. This time, instead of just being x to the 2n plus 1, it's just x to the 2n. And then the 2n factorial on the bottom. So plug in your numbers and make sure that it works. But when you plug in a 0, you get x to the 0, which is correct. And Then you plug in a 1, you get x squared. Plug in a 2, you get x to the 4th. Plug in a 3, you get x to the 6th, etc. So it does work. So once again, for cosine, just like the others, you'll have to have the sigma notation memorized and the expanded version. And eventually, someday, we are going to quiz on this, where I just give you these 5 that are from pages 11 and 12. And I'm just going to say sine x, write the Taylor polynomial and the sigma notation, and you just have to write it down. So it's literally just a memorization thing. Once you see how it's constructed, now you just need to know it. So I'm not going to attach an assignment to this one today, but I'm going to post some more notes probably tomorrow that's going to take this a step further, and then you'll have an assignment to go along with it. So thank you so much for watching. Thank you for staying caught up and copying. It was there. Leslie wants to show you something that Rose made at preschool. So we'll leave you with that. Have a good afternoon. Bye.